Hey, congratulations everyone for making it till the last video of this playlist. So in this video, we are going to look into the high-level system architecture of a key value store.
So to wind up, till now we have discussed all the technical considerations we have done for designing a key value store. So just I'll go through again once. So we have covered data partition. We have covered data replication. We have seen how do we maintain consistency. How do we handle inconsistency. How do we detect failure? How do we handle those failure, be it temporary or be it a permanent, or be it a data center failure. So all these are the building blocks of our key value store. So now let's dive into a high level view of how a read and write is being performed using the system architecture at a high level. So basically we have a client which communicates with its key value through simple APIs, let's say get key to read, put key value to write, and the request goes to the first server, which is usually the coordinator. The coordinator communicates with other servers, let's say S1, S2, and SN, S4, let's say. So coordinator acts like a proxy between the client and the key value store. These nodes are distributed on a hash ring using the consistent hashing. The system is decentralized, first of all. So let me write down the points. First, we had a coordinator. We have discussed about coordinator, what it does. Second is we have a hash ring on which the nodes are distributed. So to recap about the coordinator, it acts as a proxy between client and node servers. So the system is decentralized system, which means we can add or move the nodes automatically. We perform data replication across multiple nodes. And thereby we do not have to worry about single point of failure. There is no single point of failure, as every node has same set of responsibilities. This is an important thing which we achieve through this design. No single point of failure, since every node has the same set of responsibilities. So this is how we perform a client request from we actually do a client request to our server nodes. So let's see how does the write operation happens whenever we do a write request. So let's see what is the write path for our system architecture. So write actually happens, let's say the client wants to put some data, some key value. So this is our server. we consider the case of a single server. So it initially goes to our mem cache, or you can say consider memory cache. So before the data is being put into the memory cache, what we do is we perform a commit log, which is in the disk space of the data which is being written into. Commit log stores the transactions which happens for future references if there is any data loss or if there is any problem in the nodes. So for holding any history or any transaction which has been performed or any data which has been written to the memory or disk, we perform a commit log. The write request is persisted into the commit log. This is number one which we do. Then we write into the memory cache. The data is saved into the memory cache. And whenever the memory cache is full or it reaches a predefined threshold, let's say, so we flush the data into the disk. And in the disk, we store the key value pair in the form of a SS table. What is a SS table? SS table, or as it goes by the name, sorted string table. So this is basically a sorted list of key value pairs. So we can also learn about this in detail. If you want to read about it, I'll share the article in the description, or if you want me to make a video about it, just let me know in the comments and I'll also make a video about it. And till then you can also go through the paper. So this is a sorted list of key value pairs where the data has been flushed. So in this way our write operation has been performed. And now let's see how we do a read operation for this our system architecture which we have discussed till now. So let's see what is the read path. So now we have a server. The data is in memory, in cache, or in disk here. So the client, first what it does, it puts a read request, let's say K1, to the cache or memory you say. This is our disk space. If the data is in memory, then the data is being returned immediately from here. So there is no involvement of disk in this. If in memory, if in mem cache, memory or cache, if it's present there. So this is the first step. If not in memory, then the data is retrieved from the disk, and there is an efficient way. The cache sends the request to the Bloom filter. We use a Bloom filter. So this is basically uses a probabilistic method to check whether the key is present in the SS table. This is our SS table, as we have mentioned. It is present in the SS table or not. So this is a probabilistic way. It provides an efficient design to check whether the key is present in the node and where it might be present, and thereby reducing the time complexity of searching the entire SS table for the key. So if Bloom filters, it goes to the data request, goes to the Bloom filter. From Bloom filter, it goes into this SS table. It checks in the SS table whether the key is present in the node. If it is present, it returns the result, and this result is eventually sent to the client. And in this way, our read operation is being performed for the client. So thus, we have gone through the concepts and the techniques of designing a key value store. So if I draw a chart of what we have achieved and what we have used to achieve those goals. So if you allow me to jot down the points, what we have done. So let's revise once. So to store big data, we use consistent hashing for data partition. Secondly, availability. For availability, what we have done is data replication, multiple data center. This is for reads. Again, availability for writes, what we have done is version clock and conflict resolution. And then we have this data partition using consistent hashing. Then we have scalability, incremental scalability using consistent hashing again. We can add and remove the nodes. We have heterogeneity, that too also achieved through consistent hashing. We have this tunable consistency, if you remember, R plus W greater than N. Quorum consensus. We have quorum consensus for this. Handle failures. For temporary, we had hinted handoff. For permanent, we had Merkle tree. For temporary failure, we use sloppy quorum also, just remember this. And for data center outage, we have cross data center replication. And using all this, we can achieve our key value store design. So yeah, here we come to the end of this series of key value store. So you can go through the videos once and don't get bothered by the terms. Just remember the concepts and hopefully you will get through it and understand it very much well. Yeah, thank you for watching till now. Thank you for watching all the videos. See you in our next video.